Do the introduction again. Great. So it's a pleasure to introduce Cristian Lenart from SUNY Albany, who will speak about a combinatorial Chevalley formula for semi-infinite flag manifolds and related topics.
Okay, thank you for the invitation to speak. I'm very glad to do it, even though it's still online. I would have liked to meet everybody in person, but I'm sure there will be many opportunities in the future. So, Anders said the title of my talk. This is a joint work with my Japanese collaborators, Takafumi Kouno, Satoshi Naito, and Suke Sadaki. It's based on 3 recent papers, and we have a forthcoming one also with Dan Orr. So before going into the overview of my talk, let me just introduce the traditional Lie theory notation. So G is a semi-simple complex Lie group. We have the maximal torus T and the Borel subgroup B. The unipotent radical N. P is the traditional notation for the weight lattice, omega I the fundamental weights, P plus the dominant weights, Q the root lattice, Q check the co-root lattice, alpha I the simple roots. Then we need the group algebra of the weight lattice, which is the representation ring of the torus, with the Z basis denoted by formal exponentials e to the lambda, lambda being the weight. And the finite, W will always be the finite value. Si, the simple reflections, and W0, the longest element. So a little background. So I will be talking mostly about the T equivariant K theory. So first of all, just look at the finite generalized flag manifolds G mod B. So the T equivariant K theory as a module over the T equivariant K theory of a point, which is identified with the group algebra of the weight lattice as the basis of Schubert classes denoted OXW. So these are the classes of structure sheaves of Schubert varieties, which are indexed by Weil group elements. So now for every weight lambda, there is a line bundle, L lambda, defined like that. And the Chevalley formula just expresses the product in K theory, so the tensor product between the class of the line bundle L lambda and the Schubert class. And the expansion is in the basis of Schubert classes. And we have the equivariant parameters, E mu, equivariant coefficients. And then we get some integer coefficients, which I denote C, W, V, lambda, mu. So we know that there is such a formula, so we want to express it. In an older paper with Alex Posnikov, we gave a combinatorial formula in terms of a model, which will come up here too, called the Alkov model. You'll see why it's called like that. And then later, with Mark Shimazono, we generalized this formula to the Katz-Moody set, to Kashiwara's thick flag manifold for symmetrizable Katz-Moody groups. And here we need an infinite version of the Alkov model, which I will not mention in this talk. So now, for the purposes of this talk, I will use generalization of the Alkov model called the quantum Alkov model. And here are the things that I want to talk about, which can all be done with this combinatorial model. So first, we'll talk about the Chevalley formula for the T equivariant K theory of the semi-infinite flag manifold, denoted QG, corresponding to G. So this is sort of an affine version of the finite flag manifold, but it's a non-standard affine version. It's not the usual affine flag manifold. And this has been the subject of very interesting recent work, and especially some breakthrough by Sue Kato, which I will also mention. So that's why it's interesting at the moment to look at this flag manifold. Then we'll come back to the finite Flagg manifold G mod P and also to the partial Flagg manifold G mod P, P being a parabolic subgroup. But now we'll look at the quantum K theory, also T equivariant. And then we'll see how the results in terms of the Alkov model, quantum Alkov model, lead to very explicit computations and results in type A and hopefully also in other classical types. We can give even more explicit results derived from the uniform results for arbitrary Lie type in terms of the quantum Alkov model. And then I'll also mention interesting related combinatorics of the model, which is basically Weyl group combinatorics. Because the point is, when we go from type A, where we work a lot with tableaus, and we have a lot of combinatorics of tableaus, when you develop these uniform models for arbitrary type, this tableau combinatorics is replaced with Weyl group combinatorics, which is also very interesting. So that's a philosophy I've been using a lot in my work. And finally, if I have time, I'll also talk about an inverse Chevalley formula. So let's get started to define the object of my talk. Please feel free to interrupt whenever you want to ask something. So this is denoted QG rat. It's a reduced in scheme associated to this quotient. So we consider the group G over Laurent power series with complex coefficients, quotiented as shown there. So this has been considered by several people and studied. I indicated some of them there. And we'll mostly work with a part of this, which I can define by first introducing the semi-infinite Schubert varieties inside this semi-infinite Flagg manifold. So these are indexed by elements of the affine Weyl group. So the semi-direct product with of the finite Weyl group with the core-root lattice. And then, as I said, we concentrate on the Schubert variety indexed by the identity element. So this I'll just denote QG. So this has the usual T action and also a C star action, which is given by loop rotation. So we'll consider equivariant K theory with respect to this T cross C star action. And then the corresponding equivariant K theory has a basis over the group algebra of the weight lattice with indeterminates Q and Q inverse, has a basis of Schubert classes, where the corresponding Schubert classes are indexed now by just the positive part of the affine Weyl group, just defined as the semi-direct product with the positive part of the core-root lattice. So these are the basis elements. So now the Chevalley formula is very similar to the finite one. So it will express the tensor product of an arbitrary Schubert class with the class of a line bundle, which corresponds to a finite type weight lambda. So there's been previous work here. Kato, Naito, Sagaki gave such a formula, which is infinite for dominant weights lambda, in terms of objects that are closely related to the quantum Alkov model called quantum Lakshmi-Seshadri paths. This also came up in previous work of mine with Naito, Sagaki, Schilling, and Mark Shimozono in representation theory. Then Naito, Ora, and Sagaki gave a similar formula, which is now finite, but for anti-dominant weights, also in terms of quantum LS paths. So their idea was to exploit a connection with representation theory, namely to the level 0 extremal weight modules of affine algebras, and also use a lot of combinatorics, related combinatorics. So these things also came up in previous work of mine, as I mentioned, and Naito Sagaki, other work of theirs, and other people. So now we have a Chevalley formula due to these two papers for dominant and anti-dominant weights, and they are in terms of these quantum LS paths, which are not that combinatorial because they are actually piecewise linear paths. So the quantum Markov model, which I'm going to use, is purely combinatorial, is a discrete version of quantum LS paths. So what I've been doing with Naito Sagaki is to, first of all, take their Chevalley formulas for dominant and anti-dominant weights and translate them from quantum LS paths to the quantum Markov model. So now it's pure combinatorics of the corresponding finite vowel group. And then combining these formulas, we were able to...
amazing.
Sorry?
Oh, I'm sorry. I don't mute my...
Yeah. So combining these formulas, we were able now to give a very general formula which works for arbitrary weight lambda. Again, using combinatorics of the quantum Markov model. So first, I have to tell you what the model is, and then I'll explain the formula. So the model is based on the quantum Bruja graph, which is a graph on the finite vowel group, denoted QBGW, which has the directed labeled edges going from some element W to WS alpha, S alpha being reflection corresponding to an arbitrary root, positive root alpha. And the condition to have such an edge is we either have a cover of the Bruja order, so the length increases by 1, or we have a large decrease in length, and the decrease is specified there by twice the height of the core root minus 1. And the height of the core root, you just expand in terms of the simple core roots and sum the coefficients. So this graph originates in the Chevalley formula in quantum cohomology of finite fact varieties by Fulton Woodward. And what's interesting about it is that it has, this graph is actually very natural because it has a nice lift to the covers of the Bruja order, but on the affine vowel group. So this is has to do with the Peterson correspondence, which was made explicit and treated in detail by Lam and Shimazon. I'll mention it later. So we have this graph. So for instance, for S3, here are the covers of the Bruja order with the identity on the bottom and the longest element permutation 3 to 1 at the top. And alpha ij are the roots corresponding to the transpositions ij. And we have also the down edges. For each simple root, we have a corresponding down edge, but also here you see the transposition of 1 and 3 will take from the longest element to the identity. That's a large drop in length. So now the model starts with a finite type weight lambda, to which we associate a sequence of roots, positive or negative, which is called the lambda chain. So the roots are denoted to beta 1, beta m. And so this sequence is determined by a reduced decomposition of the unique affine vowel group element, which sends the fundamental alcove A0 to its translation by negative lambda. So basically, we can visualize this as a sequence, shortest sequence of adjacent alcoves, which start at the fundamental one and go to the translated one by negative lambda. So here is an A2 picture. You see the origin in the middle, and we have the dominant weight 310, so 3 epsilon 1 plus epsilon 2. So here at the bottom, you see the weight negative lambda, you see the alcoves, and this blue path is joining the fundamental alcove to the translated one. And the lambda chain gamma is simply obtained by recording all the hyperplanes, all the roots corresponding to the finite roots corresponding to the hyperplanes that are crossed. So here you see the root 1, 2, so epsilon 1 minus epsilon 2, then 1, 1, 3, the second hyperplane, 2, 3, the third one, and so on. And of course, there are many choices possible because there are many reduced decompositions possible. So that's a lambda chain. So given such a gamma, we'll denote by Ri the reflection corresponding to the root beta I, and Ri hat is the affine reflection. So you take also into consideration this level Li. I should say here that I only showed the picture for a dominant weight where negative lambda is anti-dominant, but you can use this for any weight. So you can go in any direction, not necessarily dominant or anti-dominant. So this will come up. So now the objects of the model are subsets of positions in this lambda chain gamma, so positions from 1 through m, which I denote J1, Js. So this is just a subset of 1 through m. And we need a certain condition. When do we pick such a subset? To show the condition, first you have to construct a chain of elements in the finite file group, starting with some fixed W, and then you multiply on the right, one by one, by the non-affine reflections corresponding to the roots in positions J1, Js. And the last element is denoted end of WNA. So here we have dependence on some fixed Weyl group element W, and also on the sequence of positions. And the condition to pick such a sequence, which leads to those subsets called W admissible subsets, is that this chain of Weyl group elements should be a path in the quantum Bruhat graph. So here the up and down steps can be in any order. So they can, this path can go up and down in any possible order. So the up and down steps can be intermingled. So now we also need certain statistics associated to this pair. And calligraphic A of W and gamma denotes all the possible choices of such W admissible subsets. And for such a pair, we have some statistics. N of A is just the number of negative roots in the corresponding positions. Weight of WA is just obtained by applying to negative lambda the corresponding affine reflections for positions J1, Js, and also the element W. A minus are those positions in the admissible subset for which we have down steps in the quantum Bruhat graph, because we saw that there are up steps and down steps which can come in any order. So if you just focus on the down steps, then you select those positions in A minus. And then the statistic down of WA is just summing the core roots corresponding to the down steps. So this is, well, I take absolute values, so I take the corresponding positive root in case the root is negative. So this is an element in QCheck plus. And finally, another statistic, height of WA, is obtained again by summing over only the down steps, these affine levels. Actually, the complementary ones, Lj tilde, is obtained by subtracting the affine level from the maximum level lambda beta check. So anyway, we have several statistics which we need in our formula. And now I can state the formula for the semi-infinite flag manifold. So you take an arbitrary weight lambda and you express it in finite weight, express it in the basis of fundamental weights with coefficients lambda I, integers. We take an arbitrary lambda chain, beta 1, beta m, denoted gamma. And then we need some decorations here by some partitions. So this set bar lambda bar is a set of I tuples. So I is the indexing set for the simple roots. So we take this I tuples of partitions indexed by the simple roots, such that the ith one is a partition of length at most the maximum of lambda I and 0. So when lambda I is negative, basically this says there is no partition. And otherwise, the partition has length at most lambda I. So the number of parts. Then chi bar is simply the sum of the total number of boxes of these partitions. And I of chi is this element in Q-check plus obtained by taking the first part of each partition as a coefficient of alpha I check and summing up. So finally, lots of notation, but now I can finally say the formula. So we take an element of the affine, positive part of the affine Weyl group, which indexes a Schubert variety. So then in this equivariant K-theory of the semi-infinite flag manifold, we can express the product of the Schubert class indexed by X with the class of the line bundle corresponding to the weight negative W0 lambda. Turns out it's easier to state it like this rather than lambda, but again, lambda is an arbitrary weight. So this expands as a sum in terms of the W admissible subsets, so objects of the quantum Markov model. And then there is also here a sum over these tuples of partitions. And then we have Schubert class indexed by an element of the affine Weyl group, which is specified there. And then we have the equivariant coefficients, E to some power and Q to some power. And you notice, so this is a more involved formula, but you see here the statistics that I defined coming up, the height, the weight, the end of that chain of Weyl group element, the down statistic, and also this I of chi that was defined up here. So it's a nice combinatorial formula expressed in terms of directly in terms of the objects of the quantum Markov model. So there is also, I mentioned here connections with the representation theory, so I'll just briefly show a representation theoretic analog of this formula. For this, we need some notation. So if mu is a dominant weight and X is an element of the affine Weyl group, then we look at the corresponding quantum affine algebra, and this has the highest weight modules, but also has these interesting level 0 extremal weight modules, V of mu, corresponding to the extremal weight mu. And then this has a certain de Mazur submodule, which is indexed by this element X in the affine Weyl group. So de Mazur module defined in the usual way as a module for the corresponding B algebra. So these modules have some graded characters, and so now let me state the analog of the Chevalley formula for these graded characters. So you take a dominant weight mu, an element of the affine Weyl group. You take an arbitrary weight lambda such that mu plus lambda is also dominant. And you also take a lambda chain gamma for that arbitrary weight lambda. And then you look at the graded character of the de Mazur module corresponding to the level 0 weight mu plus lambda and the affine Weyl group element X. And this graded character can be expressed in terms of the graded character of various de Mazur submodule, but corresponding to the weight mu. So this basically is telling you how the graded character upon this translation by lambda can be related to the graded character of the level 0 module corresponding to mu. And the sum here, the double sum here, is exactly the one from the Chevalley formula, sum over the objects of the quantum Markov model, those tuples of partitions, and you see again all these statistics: height, weight, down, and end. So you see all these statistics.
I'm sorry, I missed one thing, Christian.
Yes.
These alcove walks, since you're allowed to go up and down, are they finite or is it an infinite sum?
Yeah, these are finite. So these are always for the finite root system. So you take the alcove picture for the finite root system, and these alcove walks are shortest ones. So they correspond to reduced decompositions of the corresponding affine Weyl group element, which gives you the translated alcove by lambda.
Sorry, but I missed some subtlety. You had additional edges in this quantum W graph.
Right.
Going down, that's not showing that, so it looks like you can go around in circles. That's not happening.
It's not happening because the lambda chain is always finite. So
okay. You pick.
Yeah, I'll go back to my picture. So this chain of roots is finite. So you are taking subsequences of this chain of roots, and the condition on at each step you apply an edge of the quantum Bruhat graph.
Okay.
But there are a finite number of steps here. So
okay.
Even though you might go up and down, even though you might go up and down in quantum Bruhat graph, there are just number of steps.
Okay, good. So you're not getting rational functions in Q or something.
Right. The only infinite thing here is because of these tuples of partitions. So the first sum is finite, but the second sum, if the weight lambda is not antidominant, it's antidominant, then there are no partitions because these are always 0. But if this weight is not antidominant, then the second sum is infinite here.
Why is it infinite? I didn't understand. I mean, you're taking partitions of some bounded in each place.
Right. So these partitions, the parts, the number of parts is bounded, but
only the number of parts is the length.
Right. The length is the number of parts, but the parts
so can be. Okay, so this will produce some Q series which you have to sum because you expect to get rational coefficients. Is that right?
Right. Yeah. Well, the coefficients are always power of Q.
No, but if it's an infinite sum of a power of Q, you expect it to collapse into something like 1 over 1 minus Q. That's
yeah, maybe.
Okay. Sorry, I thought that was what you'd done. Okay, fine, but it should be happening.
Yeah. So this sum is only finite if the weight lambda is antidominant. That's the point. Okay, so now a bit of combinatorics. You see this; these formulas are expressed here in terms. I always say pick an arbitrary lambda chain. So implicit in here is the independence of the formula from the chosen lambda chain. So I'll discuss this a little bit. So some notation, which will come up in quantum K theory as well. So if you have some element in the positive part of the coroot lattice expressed in terms of the simple coroots with coefficients d1, dr, then q to the psi is simply q1 to the d1, qr to the dr. So we have here indeterminates q1, qr, which will be the quantum parameters later. So if I take a lambda chain and the quantum Markov models for that, so I take all the admissible W admissible subsets defined as before, I can define a generating function over this set of W admissible subsets for the statistics weight and height and down. So just the usual summation with indeterminate Q, the equivariant parameters for the weight, this capital Q to the down statistic, And then this is an element, end of WA is an element of the finite vowel group. So this generating function is in some group algebra of the finite vowel group. So this is essentially captures the Chevalley formula, this generating function, in a simplified way. So then implicit in the Chevalley formula is that if I have two lambda chains, gamma 1, gamma 2, then the corresponding generating functions for the statistics are the same. And turns out this can be seen combinatorially in a very nice way, and it relates to other nice things. So let me explain this. So this is a basic fact which just reduces to the fact that you can relate any two reduced decompositions by applying Coxeter moves. And lambda chains are given by reduced decompositions in the FN vowel group. So because you can relate reduced decompositions with Coxeter moves, similarly, you can relate any two lambda chains by what I call Yang-Baxter transformation. This is related to the Yang-Baxter equation. And such a transformation simply takes a subsequence of the roots, consecutive roots in the lambda chain. And if the subsequence consists of the positive roots of some rank 2 root system, then you are reversing it. You simply reverse it. And you can apply these moves repeatedly. And in this way, you can relate any two lambda chains. This is just elementary. So now the question is, how do we relate the objects of the quantum Markov model if gamma 1 and gamma 2 are related by such a Yang-Baxter transformation? Unfortunately, there is no bijection between the corresponding elements of the quantum Markov model. Unless the weight is dominant or anti-dominant. But in general, there is something called a psi-jection, a bijection between sign sets. So let me explain this. And this is constructed explicitly in a paper I wrote with Kouno and Naito. So first, there is a bijection part of it. So basically, you take a subset of the objects of the quantum Markov model for gamma 1 and another subset denoted with index 0 for gamma 2. And these two subsets are related by a sign preserving bijection. Because remember, there is also a sign associated here. In the Chevalley formula, there is also a sign denoted -1 to the n of a, if you remember. And this sign preserving bijection also preserves the statistics, all the 4 statistics. And then on the complements of these sets A0, on each of the 2 complements, there is a sign reversing involution, which also preserves the statistics. So the corresponding terms will cancel out. So this automatically says that when you do the generating function, because we have this bijection and the other terms cancel out, the generating functions will be equal to each other. So such a bijection, or together with the sign reversing involutions, is called a quantum Yang-Baxter move. So this relates the admissible subsets for gamma 1 and gamma 2. If they are related by a reversal of roots of a rank 2 root system. And as I said, this is an example of a bijection between sign sets. This concept was introduced by Ilse Fischer and Matthias von van Linka in their bijective proof of the alternating sign matrix theorem. So it's interesting that it also comes up here. And of course, if you apply this repeatedly, then you can relate any 2 lambda chains and you get the combinatorial proof of the equality of the generating functions. And I emphasize again that these bijections are constructed explicitly in our paper. There is an algorithm which constructs them explicitly. bijections and sign reversing involutions. They are all constructed explicitly. And I should also say that there is a link with representation theory, because the moves here are generalizations of the ones that I gave with my student Arthur Lubovsky, corresponding to lambda dominant and W being the identity. And in that case, there is a representation theoretic interpretation for these moves. They realize the combinatorial R matrix. So this is a unique affine crystal isomorphism, which permutes tensor factors in a tensor product of these affine crystals, Ashwara crystals called Kirillov-Reshetikhin crystals. In this case, indexed by single columns, but that's not so important. So this is these moves are realizing in a uniform root system setup this combinatorial R matrix. And if you want to think of the type A counterpart, in type A, these Kirillov-Reshetikhin crystals their elements are indexed by columns of tableaus. So increasing sequences, tensor products of them. And if you want to realize the combinatorial R matrix in terms of tableaus, it comes down to the usual jeu de taquin on columns. So in some sense, these moves that I described here are root system analogs of uniform analogs for jeu de taquin on tableaus. And here we generalize this even more, because now we can do this for arbitrary lambda and any element W. In the previous case, in the special case, we actually get bijections, actual bijections, but here we actually get sidejections. So finally, let me get to quantum K theory. So this is defined by Yuanping Li for a projective variety. So it's a quantum analog of usual K theory in the same way as quantum cohomology is a quantum analog of usual cohomology. And it's an algebra, and the product is defined in a complicated way in terms of something called the quantum K invariance of Gromov-Witten type. And it's an associative algebra. So its structure is defined by first taking the polynomial algebra in, of course, I'm going to talk for the flag variety, for the finite flag variety. So here you need quantum parameters Q1, QR, and then the group algebra of the weight lattice over this polynomial ring. So then the T equivariant quantum K theory of G mod B, the small version, is defined with additive structure being the same as for T equivariant K theory by introducing these quantum coefficients. And then this algebra has a basis over this base ring, given again by structure sheaves of Schubert varieties, which I'm going to denote O upper W. And the indexing is as usual for the finite type flag variety by elements of the finite volume. So now I can state the Chevalley formula for this T equivariant quantum K theory. This was conjectured in earlier paper of mine with Postnikov. So here we need to choose a simple root indexed by K and to fix a negative omega K chain of roots gamma. So omega K is the kth fundamental one. So then in T equivariant quantum K theory, we have a formula which is cancellation free for an arbitrary Schubert class by the class of the line bundle for negative omega K. Or equivalently, I can state it as the product with the Schubert class indexed by a simple reflection Sk, because these are closely related. The class of the line bundle with this divisor class indexed by Sk. So formula is very similar to the one for the semi-infinite flag manifold, but now it's a finite sum just over the objects of the quantum Markov model. And here you see the statistics down, weight, and end. So one statistic disappeared here, the height statistic, because that was related to the C star action, to the extra equivariant information. And the proof is, as you suspect, it's just translating from the anti-dominant Chevalley formula for the semi-infinite flag manifold via this Kato isomorphism, which is this breakthrough that I mentioned. So the Kato isomorphism gives you a relation between the equivariant quantum K-theory of the finite flag manifold and the equivariant K-theory of the semi-infinite flag manifold. This is in line with the so-called Peterson isomorphism, which is similar relation between quantum K-theory or quantum cohomology. But on the other side, you have K-theory and quantum and usual homology of the affine flag manifold, or affine Grassmann, better said. And here we have the semi-infinite flag manifold. So using this this relation, we can easily translate the previous Chevalley formula. And it's this breakthrough that made possible to finally prove this Chevalley formula here for quantum K-theory. So now I also said that I'm able to derive more explicit information in type A. So I will denote these Chevalley coefficients. So I take the Schubert class index by W multiplied with Schubert class index by simple reflection Sk. And in that expansion, I take the coefficient of Schubert class index by V times this quantum monomial corresponding to exponents d1, dn minus 1. So I take this tuple of these. And n, this n SKWVD is an integer coefficient that comes up in this multiplication. So in type A, it turns out that using the Chevalley formula and making it more explicit for type A, using a specific lambda chain, omega k chain in type A, I can show that all these coefficients are plus or minus 1 or 0. And I can say exactly which ones are plus or minus 1, and the sign is also determined. There is an algorithm here to determine exactly for which SKWVD you get plus minus 1. Moreover, in this formula, if you look at the degrees that come up with respect to component-wise order, we can show that there is a minimum degree and a maximum degree, which can be constructed explicitly. And another important thing, we can prove another older conjecture of mine with Maeno, which with Maeno we constructed so-called quantum growth and polynomials. Now we can show that these represent Schubert classes in the non-equivariant K-theory of the type A flag variety, FLM. I think I still have a little time, so I can just recall just in one slide, I'll recall how these quantum growth and polynomials are defined. So first we take the elementary symmetric polynomials of degree p in indeterminants x1, xk. So I denote them by EPK, and I can define. We can define some quantum analogs of them, denoted EPK hat, by introducing these quantum parameters q1, qn. So this is a rather complicated definition of these polynomials. But once you have them, you consider this space in the polynomial algebra over Z. You consider this subspace spanned by so-called staircase monomials, some monomials where the exponents fit inside the staircase shape. And you consider the tensor product of this with the Q coefficients. So this is some space L and Q. And on the space, we define a so-called quantization map, Q hat. So this space turns out, beside these monomials, it has a basis of standard elementary monomials. So similar indices ij of the corresponding elementary symmetric polynomials. And this monomial in the elementary symmetric polynomials is sent to the similar monomial, but in these quantum versions. So you just replace the small e with an e hat. So this is a linear map called the quantization map. And then the quantum Grothendieck polynomial, GWQ, is defined by taking the usual Grothendieck polynomial of Lascaux and Berger, which represents Schubert classes in the usual K theory of the type A flag variety, and you apply the quantization map to it. That's the construction. So this leads to a very big polynomial in general. And also recall that the usual Grothendieck polynomials are defined very explicitly in a recursive way using the usual divided difference operators. So everything here is eventually very explicit and combinatorial. And there are also combinatorial formulas for them in terms of various objects. And then the main thing about which we proved in an old paper with Maeno is that these quantum Grothendieck polynomials happen to satisfy exactly the above version of the Chevalley formula in quantum K theory that I've shown. So it just happens that if you define the polynomials in this way, you can prove, using a lot of algebra and combinatorics, you can prove that they satisfy exactly the quantum K Chevalley formula. And now, since the quantum K Chevalley formula is proved, it follows that these quantum Grothendieck polynomials do indeed represent Schubert classes. So you can multiply them. So they are polynomials representing classes in some quotient ring. So you can use these polynomials, expansion in the basis of this polynomial, to actually compute any product of Schubert classes in quantum K theory. And finally, I'll say something about the quantum K theory of partial flag manifolds. So usually you derive Chevalley formulas for K theory or whatever of partial flag manifolds first, because the formulas are simpler. But here, strangely, the process is reversed. You first do it for G mod B, and then you specialize to partial flag manifolds. So here we'll be able to give cancellation-free Chevalley formulas for quantum K theory of partial flag manifolds with additive structure defined in the usual way in the following cases. So first, we consider maximal parabolics. So we remove a single simple root K, omega K, and assume also that omega K, the fundamental weight for this K, is minuscule. And we can do this in type A, B, D, E. Such Chevalley formulas were also given by Anders, Chaput, Mihalcha, Perrin, but our formulas are of a different nature. They are in terms of the quantum Bruja graph, which didn't show up in their work. And then we can also do type C, but here we can do it for any K. So we can remove the minuscule condition. Then it's more complicated for type B and D, but we have some ideas. We are working on this also for maximal parabolics. And we can also do it in type A for two steps. So the idea is fairly simple. You start with the Chevalley formula that I've shown before for quantum K theory T equivariant for G mod B. And then there is this Kato module surjection from G mod B to G mod P. And when you apply this surjection to the formula that we derived before for G mod B, you have lots of cancellations. So you have to perform all the cancellations using the sign reversing involution. So here is the more difficult part. And once you do this, you arrive at the clean formula with no cancellations. So what do we get? Let me just show you a flavor of the formulas that come out of this procedure. So W upper J is the minimal coset representative modulo the parabolic subgroup of the Weil group. And W with the floor notation is the minimal coset representative for the coset of W. And theta is the highest root. It turns out that these formulas, what they have in common is they can be expressed in terms of W admissible subsets, which have no downstep. No downstep, this A minus are those positions where you had downsteps. So now you just want to have absolutely no downsteps, only upsteps so only covers of the Bruchau order. So that's nice that in all these cases, you don't need quantum steps anymore. Actually, you do have some quantum steps, but they are all very controlled, and you can relate them to chains for which you have no downsteps. So the first formula for minuscule fundamental weight type ABDE and maximal parabolic, you take a negative omega k chain of roots, and you take some arbitrary element in this lowest coset representatives, which index the Schubert classes. And then we have the following cancellation-free formula. Actually, we have two formulas. Here you start getting into cases. So there are these two formulas in the minuscule case for multiplying the class of the line bundle for negative omega k with an arbitrary Schubert class. So you notice down here we have a shorter formula, and up here you have a longer formula which also has a quantum parameter in it, and there is no quantum parameter in the bottom formula. And what distinguishes the two is the fact that W in the first case is greater than the lowest coset representative for the reflection for the highest root, and in the second case you have the opposite condition. So you have these longer formula or shorter formula. So here in the bottom more terms canceled out, and here these terms are left, so they don't cancel out. Finally, in type C, you can give a similar formula. Here is just one case. You have to get into some details of how this negative omega k chain looks like. I'm not going to do that. There is similar explicit formula, again cancellation free, again for any maximal parabolic here, no minuscule condition. And then for two-step flag manifolds, now you remove two simple roots, K1, K2, K1 less than K2. Here you need to take some specific negative omega k chain, which is denoted here. Ij is just the type A root epsilon I minus epsilon j. So you take the sequence of roots shown as a matrix. And here you have several cases, and the cases depend on the relative, on the relation between the values of the corresponding element of the Weil group, indexing the Schubert class at positions 1, K1, K1 plus 1, K2, K2 plus 1, and n. So there are these specified values which can lie in different orders, and depending on how the values relate here, you have four types of formulas. For the multiplication of the class for omega k1 times an arbitrary Schubert class, and similarly for omega k2. So here are the four formulas. So you have a very short formula like before, and then some longer ones, but all the formulas are just expressed in terms of chains with no downstep. So this A increasing just indicates that there is no downstep. There is, as I said, the shortest formula, then another formula which looks like this, and another one which has 2 quantum parameters in it. And then the longest formula actually has no cancellation in it. This is exactly the formula from G mod B, which is a combination of the second and the third one. So they're all very explicit. And finally, I'll just end with mentioning the inverse Chevalley formula. So this is something we are working on now with Dan Orr and Naito and Sagaki, and there's been a previous paper by them on this. So the idea here is, this is the Chevalley formula for the finite type flag variety with some coefficients. So we have 2 bases for the equivariant K-theory ring. The basis given by e to the mu times the Schubert class, but also the basis given by these products with line bundles. So you can do the opposite thing, take the ones on the right and express them in terms of the ones on the left. And Mathieu showed that the coefficients up to some change of variables are exactly the same as in the original Chevalley formula. But things are not so nice for the semi-infinite flag manifold. There is still an inverse Chevalley formula, but it's of a different nature. But it can still be expressed in terms of the quantum output model. But yeah, this is something we're still working on, and it's going to appear in the future. So I'll stop here. I went a bit over 12. Thank you.
So I clapped. My computer decided to turn off in the middle, so I don't know if anybody can hear me anymore.
Yes, we hear.
Yeah, I can hear you.
Okay, well, thanks for a very nice talk. And yeah, are there any questions?
I have a question. How much positivity were you able to prove?
Know the signs in the Chevalley formula for dominant and anti-dominant weights. So also in quantum K-theory, in all the quantum K-theory formulas, we have nice positivity. The only place where we don't know any kind of positivity or alternating property is the Chevalley formula for an arbitrary weight.
But probably there is no positivity there.
Yeah.
Is it possible to get positivity of like the product for the product of 2 Schubert divisor?
Oh, okay. In quantum K theory.
Yeah.
And I don't think it will be that easy from just the Chevalley formula, because you need more. You need to know more than just the Chevalley formula to approach general structure constants. So I don't think it will be that easy just based on this work. But you can start building on it. So there is a conjectured Pierre formula in type A in my old paper with Maeno, where we still have positivity. And I'm pretty sure we conjectured positivity there in our paper for quantum K theory of type A flag variety. And we just have it up to the Pierre level there.
Thanks.